Welcome to this webinar organized by the AutoChem Cost Action. My name is Ladislav Nagy. I am professor at the Babeș-Bolyai University of Cluj, Romania. Our speaker for today's webinar is Dr. Marco Ruberti, research fellow at the Imperial College London. Marco completed his master's degree in physics at University of Pisa in 2010. In 2011, he moved to the Imperial College London to complete his PhD, which he successfully defended in 2015 under the supervision of Dr. Aberbuk and Professor Ivanov. Since then, he was a postdoc and starting this year is a research fellow at the same institution, the Imperial College London. His research focuses on the study of fundamental ultrafast many electron processes in atoms and molecules upon excitation and ionization by ultrashort laser pulses. Recently, he independently developed a new theoretical approach of attosecond ionization dynamics of many electron systems, the restricted correlation space ADC. His current research focuses on the fundamental concepts of quantum coherence and entanglement, their role in ultrafast dynamics of photoionized systems, and in understanding the experimental observations. Before asking Marco to give his talk, I would like to inform you that if you want to ask questions, please type your questions under the menu point live Q&A visible on the right-hand side of your screen. You can type your questions during the talk or after the talk. Marco, the floor is yours.
Thank you. Thank you for the introduction. Okay. Thank you for the introduction. So let me start with outlining my talk. I'm going to do a brief introduction on the concepts of quantum coherence and entanglement in attosecond ionization of atoms and molecules. Then I'm going to describe a summary of the theoretical methodology that I developed, which is time-dependent restricted correlation space ADC, and the application to calculate mixed state of molecular ionized systems. And then I'm gonna describe a simulation of a full attosecond pump probe experiment in polyatomic molecules, both an XUV pump X-ray transit absorption experiment simulation on pyrazine, and a few femtosecond X-ray pump X-ray probe simulation on glycine using time resolve electron spectroscopy. So first of all, just to set the scene, we know that when we talk about molecules, we have different time scales depending on whether we are interested in the electronic dynamics or the nuclear dynamics, with the coherent many electron motion typically happening on the scale of hundreds to a few tens of femtoseconds. And we also know that in general, when we have a photochemical process, the 2 degrees of freedom, so electronic and nuclear, interplay in a highly correlated fashion. So we need to take into account a theoretical description of both degree of freedom to capture the physics. And in case of ionization, we also need to take into account the photoelectron that has left the ionic, the parent ion. What is interesting about quantum coherence in ionization? Well, first, it gives us an experimental testbed for proving this, for testing these concepts of entanglement and coherence in systems that are inherently open, quantum systems, and multipartite because they break in different subsystems. And second, it gives us, if we can harness these two concepts to control the outcome of these photochemical processes, it gives us a powerful tool of control by acting on the electronic degree of freedom and on the attosecond time scales, for instance. of course, we know that all this has become possible due to the experimental development that's driven also theoretical activity in the field. Recent developments include development of harmonic generation sources, which can produce very short XUV pulses, and development of attosecond X-ray pulses at free electron lasers using the X-sleep technique at LCLS in Stanford. So we have very short pulses of a duration of a few hundred attosecond, both in the X-ray and in the XUV energy range. And with this phenomenon that has been simulated theoretically back almost 15 years ago now, and has attracted lots of interest, is the so-called charge migration, right? So we have ionization of a molecule where we initially have the whole density localized on one side of the atom, of the molecule, and then the coherent motion of the system leads to the charge to migrate from one side back to the other side of the molecule, and so on and so forth, on a time scale with a period of a few femtoseconds, let's say on average, until eventually the motion is dropped by the decoherence that is given by the nuclear motion. And this the attempt, we know that attempts to reconstruct and to measure this process has been made already using different techniques and leading to great publications and great results, both from the group of Calegari and the group of Krauss, using different techniques back in 2015 and 14. So what are the goals of the field in general? So the so-called attochemistry, right? So we know that we have got this electronic quantum coherence that is now accessible experimentally, that it drives this ultra-fast charge dynamics. We know the time scales. We know that inevitably there's going to be couplings between electrons and nuclear degrees of freedom. And that, of course, when the nuclear degrees of freedom is triggered, then there is also a rearrangement of the molecular structure. It can be everything. What's the goal? The goal is to be able to do this in a controlled way. So to be able to prepare these coherences, of course, to probe them so that we know what we have produced, and then to control them, and by means of controlling them, controlling the chemical change that we have induced. So this is basically the overall goal. Now, how do we model this theoretically? So what do we start from? So first of all, we start from a photoionization process, right? So in photoionization process, we have initially a bound wave function of a many electron system. And then when we ionize it, we create this bipartite system, a photoelectron that leaves the ion, and this can give rise whether the question is, how will the final wave function look like? So will it be separable in an electronic and ionic components, or will it not? If it's separable, then we know we have coherence in each of the two subsystems. If it's not separable, then we have zero coherence in each of the two subsystems, and so they are fully entangled. So this is the basic quantum mechanics of the process, which is basically a breakup of this quantum system. So just a bit of literature. So coherence in a two-level system, ionic krypton, has been measured, and I mean the density method has been reconstructed back in 2010 between the spin orbit, two spin orbit states. And as an example of entanglement, I would like to mention the experiment performed in 2010 as well by the group of Sansone, where they ionized the hydrogen molecule with an XUV IR combination of laser fields. And they were noticing that as a function of the delay, the diffraction pattern was exhibiting some particular feature. For instance, there was an asymmetry in the they noticed an asymmetry in the dissociative ionization, and they were able to infer that this asymmetry is driven by the electronic localization, which then what does it mean? It means in the system you have a coherent superposition of gerade and ungerade state, or you don't have that. And they were able to influence this, and therefore to influence the asymmetry they were seeing by playing with the IR field, meaning the IR field interacts with the photoelectron, and therefore, because the photoelectron is entangled with the ion, also with the charge localization in the ion. And therefore, this was an example of basically entanglement between the photoelectron and the ion. So now let me come to a summary of this first introduction. So I hope I managed to consider that quantum coherence and entanglement are key concepts in attosecond science. Then when we do, well, we know that when we do time-resolved experiments, we want to capture this coherence, whether it is vibrational or electronic, we still want to capture a coherence. And we know that when we ionize a system, we produce a photoelectron and ionic pair, which are inevitably entangled. So it depends, depending on the level of entanglement, we will have also like inversely proportional level of coherence, roughly speaking. And so when we perform a measurement, coherence when we perform a measurement on each of the subsystems separately, individually. I am not talking about coincidence measurement, and I want to make this clear now. And exactly, so basically, we don't still have a full, quantum information perspective on the subject, and most importantly, on the role of electron-nuclear coupling. For example, let's imagine how cool it would be if we were able to, let's say, affect, or let's say, measure how a chemical process like a dissociation or some particular outcome is influenced by the interaction or by the entanglement between the photoelectron and the ion. So that would be cool, right? So in order to study this theoretically, we needed an ab initio framework that models the photoionization step. So we know that in a molecule, the electronic spectrum of an ion is very dense, so it has many levels depending on the size of the molecule, but in general many levels. So with a very short pulse, such as the ones that we have available, we can produce in principle coherence among many of these available states. And if we assume that we have produced coherence, still we would like to know what kind of wave function we have produced in the ion, and which in general will depend on the field parameters, right? So but most often we would we had to use approximation to estimate this initial wave function, for instance, in the earlier charge migration calculations that I showed, whose result I showed before. And one of these approximations is the famous sudden approximation, where we assume that suddenly an electron is removed from the system, and this is the mathematical expression. And the question is, when is it valid, for example? And the answer is we need a theoretical tool which models the process beyond this approximation and actually calculates this wave function. And we need to include electron correlation, of course. What are other mechanisms that need to be included in the modeling of the photoionization process? So the first, so we need to be able to, of course, describe the ionization itself. So that let's say the excitation of the electrons from bound states to the continuum. We need to describe the coupling between the photoelectron as it leaves the system and the parent ion. And we need to describe the coupling, the dipole couplings driven by the laser field between the bound states of the cation. All these effects will affect the entanglement and the coherence of our system. And in the B-spline RCS ADC theory, the way it's done is so basically the many electron Schrödinger equation is partitioned in so the ansatz is consists of two terms basically. A term which is delocalized, and so it describes ion times photoelectron type excitations in the continuum, and the term that is localized, so it describes let's say ground state and excited state of the neutral system. And the time-dependent Schrödinger equation is solved with the following ansatz. Now, each of these two parts of the wave function, so both the localized and the delocalized parts, are expanded in a configuration iteration type of expansion. So with n whole n particle excitations on the dressed ground state. And the difference with usual quantum chemistry, let's say, approaches is that instead of each of these single electron orbitals being represented in Gaussians, the basis that the single particle basis that is used is B-splines. B-splines to actually have a good representation of the continuum states. And as far as the ion is concerned, as I was mentioning before, the complex spectrum of an ionic system needs to can be described if we go beyond what is called as a Koopmans theorem. So we don't just have a removal of holes from the Artifoggan state, but in general we have a rich spectrum of states that go from the outer valence, so close to the ionization potential. Well, this picture of Koopmans is mostly valid, to a region where we have a complete breakdown of this picture, close to the double ionization potential, and where the states become more and more, the density of states becomes higher and higher. So with so for example, if we look here at possible bandwidth, we know that we can see that if we want to create coherence in the outer valence, we need a shorter pulse. Then we need, for example, if we want to create coherence in the inner valence, because in the inner valence, a longer pulse would do just a good job anyway. And then, so this is how the ionic states are described. And then, as I said, the continuum orbitals are described in these plans. Given these configurations, then we need to be the Hamiltonian, the dipole, and the complex absorbing potentials. These are just schematic representations of how these matrices look like, and there's block matrices. And well, I mean, they are 2 by 2 because the ansatz of the wave function separates the wave function into 2 parts. Now, so these are just some exemplary, some basically benchmark calculations that I did 3 years ago, when I calculated the cross section, the photoionization cross section of N2 and CO2 with the different methods. So check that the agreement was good, and it was, and that gave confidence to actually do time-dependent simulation. So in a time-dependent simulation, so of course the outcome is the time-dependent many electron wave function. So given this wave function, we need to analyze the coherence of the system. So the way we do it is we extract what is called reduced ionic density matrix. So we start from the density matrix of the system, of the n-electron system, and trace over the photoelectron degree of freedom, which we assume unobserved. So we are focusing on the ion, which is why we calculate the reduced ionic density matrix. If we want to focus on the electron, you would need to do the same and calculate the reduced electronic density matrix. Now, as an operator, it can be expanded on the, let's say, the eigenvector spaces of the ionic system. And this is the way it looks like with the ansatz, with the wave function ansatz that I showed a few slides before. Given the density matrix, what can be calculated is then the population of the cationic eigenstates and their degrees of coherence. These are basis set specific, of course, because they depend on which basis for the ionic system we are considering. While two quantities that are basis independent are the purity and the von Neumann entropy of entanglement, which regardless of the basis, they tell us how pure a state of the ion is. And they can also be calculated, of course, given the density matrix. So to summarize the theoretical ingredients that needs to be present. So we need to have a description of electron correlation and relaxation in general, if you want to describe the physics in the inner balance, mainly. We need to therefore have accurate partial cross-section to describe the process in a time-dependent fashion, and including the photoelectron. So in order to have to calculate this entanglement with the ion, and also have the interchannel couplings in the continuum in taking into account. Ideally, we would like to model Auger decay, for example, but this can be done in a sequentially, so in a two-step model, because we only can afford one electron in the continuum in this method. And ideally, we would also like to describe the coupling to nuclear motion using either MCTDH or RMFS method, which this will give us a complete description of the process. Unfortunately, this is not done yet by me, at least. So I'm going to talk about, let's say, the electronic modeling of the process. So let's start from an IR-pump VUV-probe in CO2. So in CO2, when we ionize it with an IR pump, we can produce several the ionic system in several eigenstates. Then, so the way the simulation is done is we take this wavefunction, we take the density matrix of the ion as it has been calculated by the simulation of the pump, and we plug it in the simulation for the ion interacting with the probe. And in this case, given this for symmetry reasons, the probe consists of two frequencies, let's say omega and 2 omega. For a general molecule, this wouldn't be necessary. And by doing this, we calculate the total yield of 2+ decations. So the results of this the following. So we studied how the coherence evolves by changing the carrier frequency of the pump and the intensity, and we studied also how different mechanisms impact the coherence by removing artificially from the code different contributions to the Hamiltonians and dipoles. And in general, the result of the probe simulation was telling us that we have a total yield of CO2+ decation that oscillates, reflecting the degree of coherence that had been induced at the pump stage. So this was the first, let's say, the results of the first theoretical simulation that we did using the B-spline ADC code as a first test. And then I moved to more complex systems. So of course, I moved to XUV pulses. And when you talk about XUV pulses, inevitably you talk about ionizing also in the inner valence. So we don't have, with an IR, you ionize only basically in the outer valence. But with an XUV, you start affecting the inner valence. And as I was saying, so a region where the density of states is much higher, so where you have to describe electron correlation, and so where you have many more states. So here you can see a map, a 2D map of the degree of coherence between each pair of ionic states, calculated for C2H4 molecule. And given that So why is it necessary to describe these states accurately? It is because when then we calculate the let's say charge dynamics triggering the system by the ionization, what we can see is that what dominates is the correlation-driven charge dynamics, which is driven by exactly these inner valence states. So with an XUV pulse, they need to be taken into account to have a proper description of the induced dynamics. What about an X-ray? What about now the probe? So if we have ionized the system, like with an XUV, for instance, produce this charge dynamics, and we want to probe it. And we want to probe with an X-ray, because we now have because they have high intensity, so they give good signal. There's just been an X-lead demonstration a year ago at LCLS. So we have two techniques we have two possible strategies to probe with an X-ray. We can probe using attosecond transit absorption. So we ionize the system, and when we absorb from a core, we excite from the core to the hole that we have produced. Or we can do a measurement in X-ray and photoelectron spectroscopy type of setting, both using core XPS or valence XPS. So both of these strategies will give you, in principle, will be sensitive to the coherence in the ionic state that we have produced with the pump ionization. And now I'm going to present just two examples of two simulations of both of these two settings. First setting, so we said, is attosecond transit absorption. So we have a UV pump ionization of pyrazine and then X-ray probe. The cation is X-ray probed in a transit absorption setting. This is the bandwidth of the pump, this red line. And these are the ionics, the population of the ionic states of pyrazine as it results from the pump simulation. For each of the pair of those states in the coherence is calculated, and also the relative phases between the two. So both the real, let's say the real and imaginary part of the density matrix. So once the density matrix is produced, we can calculate the of the ion, we can calculate the charge dynamics in the ion. I'm gonna skip the details of how it looks like, because it's beyond the point I want to make. Now, what about the photoelectron and ionic entanglement? So that, as I was saying, in order to estimate that in a basis independent way, the quantities that need to be calculated are the purity and the von Neumann entropy. And as you can see, as time goes by, so as the photoelectron leaves the system, the coherence decreases and the entanglement increases. This is a generic feature of a breakup of a quantum system. And this happens mainly in the first femtosecond. Then the two quantities kind of become kind of stable. And then, so what is the let's say the most clever thing that can be done when we have a density matrix is what you usually do with every matrix, so to diagonalize it. So if we diagonalize the density matrix, it's what people call Schmidt decomposition or purification. And you end up finding a set of eigenstates, which are the so-called coherent channels, and the eigenvalues is going to be their weight. So how much they count in the process that you have triggered, basically. And so each of these coherent channels do not talk to one another. And so you can describe you can forget about their interaction and describe, and basically it's like having n systems who don't talk to one another, and each of them is a pure state. And in this case, there were basically 10 coherent channels contributing. So this simplifies from having tens of possible states and coherences to having 10 pure states that we know exactly how they look like. And then once you have these pure states, you can propagate, you can use it to solve the time-dependent von Neumann equation for the density matrix, and with two probes, one resonant with the carbon K edge absorption and one with the nitrogen K edge absorption. And this will give you a time-dependent signal. And most importantly, when you do a Fourier transform of the signal, you will get a map of peaks that corresponds to all the coherences in the pure states of the density matrix decomposition. So when you compute the attosecond transit absorption signal, you do the Fourier transform, and then you can relate each of these peaks with what was calculated to be the Schmidt decomposition, the coherences in the Schmidt decomposition of the density matrix. So basically, this tells you, if you do a transit absorption measurement, how many of these coherences you can actually image. And the answer is, depending on your, of course, experimental error and capability, in principle, quite a lot. So just to summarize this part, the method, the time-dependent Bisprine HCS-DC method applies to polyatomic molecules that describe electrocorrelation. We know it can allow us to calculate quantum coherence and entanglement information ab initio, and allows to perform ab initio simulation of pump probe experiments. And the X-ray transit absorption setup is very powerful to capture these quantum coherences, especially if with very short pulses, such as the ones that are available at LCLS. Now, what about the XPS setting? So here I'm going to describe the simulation only of an experiment that's been performed by the group of Till Larmar. So this is a project that is led by the Till Larmar group, and the experiment was done at Flash. So we have glycine, and we have an X-ray pulse, 270, femtosecond duration, like 5 femtosecond duration X-ray pulse with frequency 274 eV. We split it and we delay the two. So we have two identical pulses. One serves as pump and the other as probe. And there are two mechanisms that can happen. So one mechanism is we ionize the system. And then we have, for example, if we ionize from 10A prime, then we have the transit absorption signal. So we have an excitation from the core back to fill the hole in 10A prime and a consequent Auger decay. So let's say we can measure in principle the Auger electron emission, which would be a sort of attosecond absorption experiment. Or we can measure directly we have a second photo emission direct. So from the state that we produce with the pump, another photoelectron is promoted to the continuum. So there are two possible processes that happen in this kind of experiment. And the result of the experiment, which have been confirmed by the simulation with the spline DC theory, is that they were seeing there is a signal, an oscillation of the electron yield with a periodicity of around 20 femtoseconds. And feature of this experiment is that this oscillation has a phase which is dependent on the photoelectron kinetic energy. In particular, there is a switch of phase of by pi at some kinetic energy of the photoelectron. And this is reproduced by the theory. So how does the theory work in this case? So again, we have glycine. So we let's say solve the time-dependent Schrödinger equation for the first pump photoionization process, calculate the density matrix, so which gives us the coherences here on the left and the phases on the right. And as you see, the highest, the strongest island of coherence highlighted here on the left is corresponds to the 10 prime states. So the 10 prime states are the states where 10 prime, I say states because of course there is a band of, it's a band of states which all have a contribution from the 10 prime orbital, are the states which exhibit the strongest coherence. This is basically due to the bandwidth of the pulse. It's quite a long pulse, so short bandwidth, and so coherence between outer valence state is not strong. Why is strong in the 10 prime? So we have coherence between this, these states in the 10 prime region, and we also know that nuclear motion, which I haven't mentioned so far, actually plays a role. And so a potential mechanism in which nuclear degree of freedom can decohere, the electronic coherence is by the dephasing that comes from the spread of the initial nuclear wave function. And so in order to calculate this, we need to basically average the result of a single geometry calculation over the quantum distribution of the initial nuclear wave function. As we do this, we obtain, let's say, a survival probability of this state that evolves still showing some time dependence. So over, let's say, 20-25 femtoseconds. So this shows that inclusion of this spread of the initial nuclear wave function doesn't destroy the electronic coherence in the 10 prime band. So this was this is a way to check that a single geometry calculation makes sense, or still produces some coherence that it can be visible in an experiment. And then the probe needs to be simulated. So in this case, the probe is again X-ray ionization of the ion. So we have again we start from the density matrix of the ion. We do a Schmidt decomposition of it, and then we have all these ionic pure channels. And for each of these pure channels, we solve the time-dependent Schrödinger equation of them interacting with the probe. So we expand them in a linear superposition of ionized decationic state and the bound ionic state. And when we do this, we can then calculate the photoelectron yield of this process, of the probe process. And as you see, the calculation shows a yield that oscillates as a function of the time delay between pump and probe, with two different phases depending on the energy of the photoelectron. And as I was saying before, there are two possible mechanisms, right? One is core excitation, core resonant excitation, and then Auger decay, and the other is direct photoemission of an electron. And in this case, the Auger mechanisms contributes in a very minor way. So mainly what we are detecting, if we were to do an experiment like group of Tim Larman did, we will be detecting directly emitted, so sequential photoionization driven by the probe. So we will be doing an experiment in XPS setting, basically. And if we want to then understand which coherences we are imaging by looking at our signal, then we need to compare how the signal oscillates depending on the ionic pure channel that we are considering. So given that we have this Schmidt decomposition, we can solve the probe equations for each of these pure channels. And as a result is that the 10 prime is the one which mainly contributes, as it is like to be expected, given that is the channel where the highest coherence is present in the first place. But nevertheless, of course, in principle, all of them have a contribution that needs to be summed up to obtain the signal that is measured in the laboratory, basically. And I don't know how much time I have left, but this was my last slide. So thank you for your attention.
Thank you very much for this very nice talk. Do we have some questions? I do not see any questions. You did not type questions here. Well, interesting results, Marco. I have a question from your introduction. You have said that the entanglement decreases the coherence. Could you explain this? Why?
So, yes, let me go back to the slide. So basically, the definition itself of entanglement and coherence are such that they're kind of, you would say, if they were like really, this is that. So you see this state here on the left, the one highlighted in blue. This is fully coherent in the sense that the full wave function is separable. It's actually factorized as a part that is fully involving the ionic coordinates, and the other one who is fully involved, which is fully involving the electronic coordinates. So the two are factorized. So it's possible to identify a term which is only about the ion and a term which is only about the photoelectron. So we have coherence. And because the coherence is because if we have a wave function, we then, for example, the ion, then we have exactly a pure state or a coherent superposition of states. So of course the coherence is maximum. Every pure state is fully coherent. Now, by definition, this is not entangled because the entanglement the entanglement is zero for a separable state. So if you want entanglement, to maximize the entanglement, then you would have something like the green case, where you have the typical qubit Bell state, let's say I times 1 plus j times 2. And there's no way to factorize this into a term which only involves I and j, and a term that only involves 1 and 2. Because 1 is different from 2 and I is different from j. And so here we have perfect entanglement. The coherence is 0. There is no way to factorize it, so there is no way to have a wave function. No wave function, no coherence superposition, no coherence. So the two things are kind of one excludes the other.
Thank you, that's clear. I see that we have some questions on the chat. So there is questions from Gilbert Grell regarding the Auger decay in glycine. Precisely how the Auger decay contribution has been evaluated. Yeah.
So the Auger decay contribution. So this is very technical question. So sorry, the answer is going to be quite technical. So it is evaluated by, in the simulation, there is a complex absorbing potential, which absorbs the wave function as the wave function hits the boundary, right, of the grid. Now, the directly emitted photoelectron is very fast because we are talking about 260, 250 eV, and it hits the boundary almost immediately, like after a few hundreds of attoseconds, and then it's absorbed. and then that it's gone. But in the simulation, there is still the Auger decay who produces a photoelectron wave packet and much more slowly hits the boundary, right? And so by only considering this let's say absorption by the compensatory potential, it's possible to only identify the Auger contribution. This is one way. The other way is to basically exclude from the simulation the possibility of directly emitting a photoelectron. So artificially setting to zero some dipole matrix element, and so to enforce the fact that only the Auger process has to happen in the simulation, and then let's check what is the yield, and then do the other way around. So disenable the possibility of Auger and only enforce the direct photoelectron, and then compare the two. This is another way of doing it. We did both, and the result was the same.
Thank you.
Oh.
Kiyoshi Ueda has written here that in the glycine, I understand that the spread of the ground state vibrational wave function does not cause decoherence. But what about the nuclear motion that takes place in 20 femtoseconds?
From the theoretical point of view, the answer is I don't know, because that was not, I didn't do a calculation in which I included this effect. So from the theoretical point of view, I would say I don't know. From the experimental point of view, I would say it does not, because otherwise, because if it did this completely destroy the coherence, then the result of the measurement would not have been to detect this oscillating signal, which matches the theoretical calculation very well. So let's say empirically, I would say it does not destroy this coherence. Theoretically, I cannot say because I didn't do the simulation.
Okay. Mark Recking has a question or comment. Very nice talk, Marco. You mentioned that so far nuclear dynamics is not included. Can you describe what needs to be done in order to include this? And to what extent you will be able to simulate systems with similar complexity as the ones of you have looked at so far?
Yeah, so thank you. So what would need to be done is to couple the first of all is to select a method for nuclear dynamics, and then basically couple so let's say like interface it with the electronic wave function that is calculated by this spline DC. So we've got as a result an ionic state, which is a linear superposition, which is incoherent superposition of pure channels. So each pure channel is a linear superposition of ionic states. And given this linear superposition ionic states, you can use quantum chemistry nuclear motion method that, let's say, as an initial guess for the electronic wave function that state that is given as output by the spline DC simulation. That would be the first thing that could be done. And in terms of the systems, then it depends on how many, let's say, degree of freedom, or how many potential energy surfaces can be handled by the nuclear motion method that is chosen. So it's down. So let's say how much it can be extended to nuclear motion, then it's just so to which system is just about the capability of the nuclear motion method itself. So yeah, so it's if the nuclear motion can handle that system with that number of let's say normal modes, then fine, then it can be done. If it cannot, then it cannot be done. But it's down to what the nuclear motion method can do.
Okay, I do not see any other questions. So thank you again, Marco, for this nice talk and clear explanations. And thank you for all for participating. Thank you. And bye.
Thank you. Bye.